Well, ladies and gentlemen, moving right along, please join me in welcoming our plenary speakers. Ladies and gentlemen, it is now my pleasure to introduce and welcome our plenary speakers of Icon Smart 2020. Professor Negami was graduated in Tokyo Institute of Technology and now working in Yokohama National University as the Executive Director and Vice President for Education and Publicity. He is a mathematician, which is a pioneer of topological graph theory in Japan and working for reformation of mathematics education. Dr. Ariel Lippmann, PhD. Dr. Ariel holds a PhD in physics from the University of Queensland and a Master in physics from Auckland University. Dr. Ariel is a Deputy Director of the Monash Energy, Material and System Institute and Director of Energy and Carbon Programs at the Monash Faculty of Information Technology. Dr. Ariel is an energy material expert and energy market specialist with experience across all aspects of the electricity supply chain. Dr. Ariel's core interest and specialty is modeling and simulation of electricity system and market using high-performance computing platforms such as computing clouds. Professor Dr. Benjamin Chersil. Professor Chersil holds a PhD and Master in Biotechnology Engineering from Osaka University and a Bachelor in Chemical Engineering from Tohoku University. Professor Chersil's core interest and specialty is biotechnology, bioprocess engineering, enzyme technology, fermentation, modeling, and simulation. Dr. Prasad Kaparaju. Dr. Kaparaju heads the Environmental Bioprocess and Biotechnology Research Group within Civil and Environmental Engineering Discipline, School and Engineering and Built Environment, Griffith University, Australia. Dr. Kaparaju has over 20 years research experience in the field of renewable energy, organic waste management, and environmental biotechnology. Professor Dr. Muhammad Basharuddin Abdul Rahman. Professor Basharuddin Rahman is currently the Senior Professor of Chemistry at University Putra Malaysia and was appointed as Distinguished Visiting Scholar at the University of California, Berkeley. He received his PhD in catalyst chemistry at the University of Southampton. His research area include biocatalysis, chemical biology, computational chemistry, and nanobiotechnology. Ladies and gentlemen, for your information, the plenary speakers will be moderated by Professor Julius Ponto, Master of Science, and Insinyur Fekim Reki Mandiri, Master of Science, PhD. And it is now my pleasure to introduce our moderator. Professor Julius Ponto, MSc, is a professor in biochemistry at the Department of Chemistry, Samratulangi University. He is teaching biochemistry, enzymology, analytical chemistry, and food chemistry. He has a master's degree and PhD in food chemistry and enzymology from University of Saskatchewan, Canada. His fields of expertise and research interests include sugar palm and coconut oil processing, and their quality analysis, and the physiology of palm sugar tree. He is also interested in fish oil quality, especially the omega-3 fatty acid. Feki Reki Mantiri PhD is a senior lecturer and vice dean for academic and collaboration affairs of the Faculty of Mathematics and Natural Sciences, Samratulangi University, Manado, Indonesia. He is also the chairman of the organizing committee of the Icon Smart 2020. He holds a PhD in the biological sciences from the University of Newcastle, Australia, and Master of Science in Molecular Biology and Biochemistry from Simon Fraser University, Canada. Fields of expertise and research interests include molecular biology, environmental biotechnology, and bioinformatics. Well, Professor Julius and Mr. Feki Mantiri, PhD, we'd love to hear from you.
Okay, thank you very much, Dr. Susan Mambu, for the introduction. Thank you, committee, for the honor that's given to me as a moderator for this precious international conference on natural sciences, mathematics, application, research, and technology, Icon Smart 2020. Ladies and gentlemen, before we proceed to the session, I would like to remind for the honorable speaker that you have 20 minutes for the presentation, and the question and answering session will be at the end of this session. We will have about 30 minutes for that. Ladies and gentlemen, and please, for the participant who wanna have a question, please write it on the share screen, and then moderator will be read that at the end of the session. And we will, and if have the time, we will have direct question. Thank you. Ladies and gentlemen, the first speaker for this plenary session is Dr. Ariel Lippman from Monash University, Melbourne, Australia. He will speak about energy. Please, Dr. Ariel Lippman, the stage is yours.
Thank you, Pak Julius. Welcome everyone. I'm very pleased to be here again. Although not physically this time. I'd like to thank Pak Feki for inviting me, also Pak Benny. I look forward to one day being at the physical venue again someday to meet you all in person. And I very much enjoy my time in Manado and working with various colleagues and various projects from Unsrat and others. So just check if do I need to keep an eye on the chat at all? See there's a few messages, but maybe that's for the others. And so, yes, I'm going to talk about something sounds a little bit esoteric, optimization, machine learning, and AI for rapid grid decarbonization. And I'll explain in a while, why that is. So basically, what we do is we look at how do we plan the energy system of the future? How do we model the energy system of the future with computer models and mathematical models, not fashion models, of course. And so we will, I'll go on and describe a little bit about that. But why are we doing it? So what's driving our work at Monash and at the Monash Energy Institute, and also across all my colleagues in Indonesia and Australia in this, and this is the climate challenge, right? We have a major problematic trend that's affecting all of us equally around the world. It is, carbon dioxide is a great greenhouse gas. It serves to regulate the temperature of the earth, both for good and for bad, depending on how much there is there. And humans have been putting more CO2 into the atmosphere for some time. about 150 to about 250 years. And the challenge is now, how do we stop doing that fast so that we don't warm the world too much? So the climate science tells us that we need to arrest warming at 1.5 degrees above pre-industrial levels, or we will face runaway climate change. And that's because the climate is a nonlinear system with feedback. And once it tips over into another regime, it's very hard to bring it back. It takes decades, if not hundreds of years. But we've got a window of about 10 years to do this. And this is what the climate science tells us. Emissions have been increasing and increasingly fast since the 1960s. A lot of us today are in one way or another contributing to this. And so we here at Monash and the Monash Energy Institute and our colleagues around the world are trying to work out how to mitigate this. And what the climate science tells us is, and this is from the United Nations Framework for Climate Change, is that emissions need to start reducing globally by 2020 and need to be at about 50% below 2020 levels by 2030 to meet these climate challenges. So this is the most urgent problem facing humanity today, in my view. And the atmosphere is shared by all of us, so we can't compartmentalize. So we all need to work together to do this. So where do modeling come in? Well, a lot of the emissions come from the electricity sector, right? So electricity was a grid, is a grid where we burn fossil fuels, large amounts of them, fossil fuels that took millions of years to trap in the Earth's surface. And now we're throwing them out in days, years, decades. And so that grid is also designed for one-way power flows from the large power station through to the centers. Now, interestingly enough, we are running out of fossil fuels. If you look at the commodity prices for oil, gas, and coal, since the 1970s and 80s, you can see that the prices have been increasing exponentially. That means we really are running out, and so we need to find alternatives, both for economic reasons and for climate reasons. We have different countries have different economic growth trajectories, and we need to take that into account. And so there's an opportunity to stage the decarbonization where emerging economies take a little bit less time, can take a bit longer to go about it. However, we are running out of time, and everybody collectively somehow needs to reduce emissions by 50% by 2030. So there's no time to grow emissions. And some of the work that I'll talk about is how the work we've done based on the work for Australia, and we did some work for Indonesia to show how Indonesia can do this. The solution, of course, is to still use the old grid. The old grid is very useful for moving power around. Add some intelligence to it. Smart grid is one such solution. Luckily, we also have very cheap renewable technologies now. In fact, in most places in the world, and I would assert quite strongly that even in Indonesia, it is cheaper to build and operate a new solar farm or even a wind farm than it is to build and operate a coal station, even with Indonesia's coal competitiveness advantage. That's the same for Australia. We're not building any more coal generation or gas or anything else because it's just too expensive and also it has emissions. So the Fusion Network is an interesting network of collaborative energy resources that's underpinned a lot more by intelligence, by computer science, computer technologies. And if you look at the International Energy Agency and other agencies, they're forecasting huge amount of investment in infrastructure that is not fuel supply based over the next years. Some of this is probably even out of date now, and nobody will really build any new coal-fired power stations if they look at the economics of it and the climate of it. There are still some governments around the world who have some interest in this, and in some cases it may make sense, but these technologies will become stranded assets in the near term. So if you build a coal station now, it doesn't have a lifetime of more than 10 years before it becomes obsolete. I'm not going to talk too much about or anything about the COVID impacts on the energy system, but I would invite you to join a a seminar that we are hosting as part of the Australian Energy Research Institutes Council, ERICA, and Monash is chairing this council at the moment, and we will be having a talk on the 28th of October, 4 to 5 p.m. Australian Eastern Standard Time, and I can share that later. So just jumping into a bit of technical discussion. Basically, our goal here at the Monash Energy Institute, the Monash Grid Innovation Hub, and other initiatives we're part of is to show and make sure that it happens. 100% renewable electricity grid is possible by 2035 or even earlier using the right tools. Most of these new tools are in the fields of information technology and computer science, and joined together with electrical engineering technologies such as transformers, smart transformers, power inverters and power converters, and combining with good government and market regulations. So at the Monash Energy Institute, we look at a lot of these things. And what we do is do a lot of cross-disciplinary work. We have IT and computer science, we have engineering, we have economics, econometrics, business law, and marketing. And then we have our buildings and properties division, which does this locally on our campus. So we have some themes we focus on. We focus on advancing new energy solutions, new technologies, helping the system transform. This is where my talk is today, making sure that the consumer is looked after and not just regarded as an asset for the energy supply sector, and then enabling energy access in remote areas like parts of Indonesia and Africa and India. There's still 1.2 billion people without electricity. These are several initiatives that I work on and we've worked on. And the most relevant one to mention is the Net Zero initiative, which we work together with various industry partners. So we have a very close relationship with industry partners at Monash. So what we are doing is, instead of just doing modeling, which is great, we also are doing making our campus net zero, and the Vice Chancellor, our Rector, has committed 3 years ago to make the campus net zero by 2030. We are well on the way there, and we're doing this in accommodation researchers and the buildings and property division, the facilities managers of our campus. And how are we doing this? Well, we realized that basically we're forecasting some significant student growth. Of course, this will need to be revised under a COVID scenario. And we're expecting that our cost to provide energy will increase dramatically. And in fact, we showed that it's cheaper to go net zero than to keep using electricity the way we were using it. And we got a UN award for this. 2 years ago, we accepted that, and a UN Lighthouse Award for climate change. And we're going to be working around the world to show how this can be done, working with other universities, particularly Indonesian universities through our newly established, or in the process of being established, Jakarta campus, the first international campus in the world for a university. And we, for example, in Monash, we will be sourcing all our electricity from a wind farm, not on site. We can't fit that many turbines on site, but we also have solar panels which meet some of our load. So we're also making the campus into a living laboratory where we can show how we can actually manage these new technologies locally, work with industry partners and academics and students as a kind of experimental lab. And here you see our campus in Clayton, and all these purple buildings here are ones that are going to be enabled soon with some AI-based devices, which will help them manage their load in response to changing conditions on the grid. And that helps you to balance when it will ultimately work. It'll help us balance renewables that are variable. So as we go forward in time, renewables on generation becomes much less controllable because it's large-scale wind and solar, which pretty much will dominate the electricity grids of the future, large-scale wind and solar farms. And even in Indonesia, where you perhaps don't have as good wind resources, I ultimately see quite significant amount of wind, some of it onshore, some of it offshore. I will, for the interest of time, I'll just move on. Some of the people that have been having a look at some of our new infrastructure, and please come to our website and find out a bit more. Now, we visualize our campus, we simulate and model and visualize. So visualization is a way of communicating changes in infrastructure and dynamically and over long periods of time. And so we are working very closely between different parts of the university to show how we can understand our energy use and how we can then show what changes in energy use will look like and help decision makers make better informed decisions. We have several facilities that are being deployed on campus. We have a battery or 2 batteries will be deployed on this part of the campus. Our buildings will be able to increase and decrease their consumption in response to signals. We have rooftop solar. We will have a total on our campus of 4 megawatts of solar. And then we will also have electric vehicle charging stations. So from computer science to digital energy, or from computer science and electrical engineering to artificial intelligence and data science for a smarter, lower carbon grid. This is what we are focusing on at Monash across the board, and in my faculty of IT and in my department of data science and AI in particular. So our faculty has several areas of focus: data science and AI. You can see on the left here, which includes optimization and machine learning, not just machine learning. Computer-human interaction and creativity, so much more like working with humans the way we work in day-to-day life. Not everybody is a programmer, and nobody ever will be a programmer. We have cybersecurity and other systems design, and then we have organizational and social informatics as another area where we spend a lot of our time understanding how people and computers relate to each other. And these are the sort of 3 major areas within our data science and AI group, which we apply to electricity and energy market, energy system transformation. So I'm going to show a little example of some of the ways we do this. I will show you a look at a high level model first. Very briefly, what we have is we have these grids of the past and the future. We have cities, we have countries, we have existing coal and gas-fired stations, and we are adding to these new resources like wind, solar, and storage. And the thing is, you can see here in the graph that the solar is in green here, the wind is in red, and the controllable generation is in blue. So we're going to get more and more of the red and green and less of the controllable in blue. That means we have to be much cleverer in the way we design our grids. And our grids are networks of energy sharing between different parts of the country, and we need to figure out how to make this network work with a completely different configuration of generation and new lines. So what we do is, this work is primarily being done by one of my ex-students, who's now a research fellow funded by Monash's, Australia's main scientific and industrial research agency, CSIRO, and its digital Data 61. And so Samini is doing work on this to enhance the tools that energy system planners, such as PLN and Australia's energy market operator, use. And so she works together with a team of expert optimization specialists and energy market specialists. So I will very just briefly show you how this actually looks. This is our grid now, and this is sort of simulates what our grid how a grid will change with coal-fired or gas-fired power stations and some loads where the black circles are. And now we're going to put in more wind and solar, and then we are going to need more transmission to get the energy to move around. And then we have to model how the balance of supply and demand works. We have demand, we have supply, and we need to figure out how to use the existing generation, which is still fossil fuel, to meet that difference between demand and the uncontrollable supply. And some of that can be done through storage. Some of it can actually be done through building more transmission to allow more energy to move around more flexibly. Given the time, I will skip through these more detailed problem formulation slides and move on to a case study which is relevant to Indonesia. And we'll briefly review that, and then we can have some, you can ask some questions, and I can share more information with anyone who's interested later. So this was a project done under the auspices of the Australia-Indonesia Centre, which is...
we have 3 more minutes.
Thanks. So we have the Australia-Indonesia Centre was founded by SBY and Prime Minister Tony Abbott in 2014. And we worked for about 5 years on various aspects of energy together with colleagues from across Indonesia, including our co-leads, Bu Ulfa and Bu Retno from IPB and ITB, but we also did some work with our colleagues at UNSRAT as well towards the end of it. And so in this project, we said, what if we seriously looked at how much renewable energy we can put into the Indonesian system, primarily focusing this study on Java, Bali, and Sumatra, because that's where 80+% of the electricity is consumed. But we were hoping to go on to do the modeling for all of Sulawesi, Kalimantan, and Eastern Indonesia, Maluku, East Nusa Tenggara, and so forth. So we based this on an Indonesian plan. The Indonesian energy company PLN, which has 10-year plans. Every year it updates them. We said, well, what if this plan was actually modified to head towards 50% renewables? Is this possible? And how much will it cost? And the good news is it's possible, and it actually will cost no more than the existing plan, but will be 50% more or less lower in emissions. The way we did that was we used some sophisticated AI and optimization tools that are available off the shelf. They're available for system planners like PLN. We wanted to use existing tools to show that you can even do this modeling without doing any much additional research. And so there is some information about how this Plexos tool works, and you put in different scenario assumptions, you put in your existing generation and transmission infrastructure into the model, and you put in your demand forecasts, and then you do put in some possible future plant and that will be built, like wind and solar, natural gas as well, and coal. We put in all of them to see what's the optimal, i.e. cheapest solution that maintains system reliability. That means power always remains available when it's needed up to a certain level of reliability. We reviewed the forecasts of demand, and we noticed that traditionally PLN tends to over-forecast demand growth. All these dashed lines are the forecast for, on the left, Java, Bali, and then on the right, Sumatra. And the black lines here are what actually happened. And so, in fact, Indonesia's demand never turns out to grow as much as people predict at any time. And that's because things are becoming more energy efficient, and also perhaps people are always optimistic about how much economic growth will actually happen. And so, big lesson on this slide, there's 2 lessons from this whole talk. One of them is, don't build to your forecast, in at least when you are forecasting based on economic growth targets, which tends to happen, because you will build things you don't need and you will waste money. That's not something a developing country, a middle-income country like Indonesia needs to do and can afford to do. So we revised the forecast, put them into our model, put some other things into our model, like the current stock of generation in every province that we are interested in.
Extra 2 minutes, please.
Thank you. Yes, I will finish in about 2 minutes, and then we can do the Q&A. And we put that in. We put in the retirements. That means power stations going to be turned off. We put in the transmission grid. So East Java to Bali, there's a transmission line that will be expanded. Existing transmission lines. And then we looked at various ways of quantifying how an investment is valued, a weighted average cost of capital, which includes things like interest rates and so forth. And we put in I did an analysis of the resource potential, and we threw it into the model and did various scenarios and found some very interesting things, basically. So we first of all said, well, what's an optimized version of the plan, the RUPTL? look like. And we showed that you can, even just being a bit more optimized about the plan, you can save $10 billion over a 10-year horizon. And what we then did is we said, well, what if you actually allow to build a lot of renewables? And then we showed that basically you can have a system with about 43% renewables in Indonesia, or Java, Bali, and Sumatra at least, and the same is possible most likely for Sulawesi by 2027. So, and this shows the mix of energy or capacity for solar, wind, hydro, and biomass. And then we showed at the end that compared with, this is the AUPTL, if you build all the plant that PLN was planning to build, this is from the 2017 AUPTL, it'll cost about 152 billion. And then we showed that depending on various cost assumptions, the actual cost of a high renewable will be lower than that, slightly higher than an optimized version of the AUPTL, but also we did some scenarios around if technology costs will reduce quicker than expected, which they usually do, then it'll actually be cheaper. So yes, thank you very much. That is the end of my talk. There are some graphs to show how this looks like in real time. And then the general insight is there are significant risks of overbuild if forecasts are overstated. That means over-forecasting. Renewable energy can be a cheap system, at least even in the short term, and going further, there is also a very strong hope that we can do that. And planning and policy is critical to this. So just because we know this is technologically and economically possible, doesn't mean the rules of the game are appropriate. And then we also have the tools and solutions to make this happen. And this was funded by the European Climate Foundation and sponsored by Institute of Essential Services Reform, IESR, run by Fabi Tumewa and Egi Gakara and Agustam Bolon. My apologies. And my colleagues from Germany who supported that. So thank you very much.
Okay, thank you very much, Dr. Ariel Lippman, for the very interesting presentation. Okay, and I remind for the participant who want to ask questions, please write on the share screen, and then will be answered later on at the end of the session. And in case of the presenter cannot be here anymore, the committee will arrange for the online answering. Okay, thank you very much again for Dr. Ariel Lippman. The next speaker is Professor Dr. Seiya Negami from Yokohama National University, Yokohama, Japan. He will be presented in the recording mode, and please the committee, the technician to leave it up.
Well, this is Seiya Negami speaking from Yokohama National University in Japan. First, I would like to my thanks for organizers of Icon Smart. They give me a second opportunity to talk about my work for Indonesian people. But I'm so sad I have to stay in Japan. I can't go your country. Well, the title of my talk is Beans Functions. Nobody knows. As a mathematical model for a social distance. Okay, so the story I'm talking about today has begun a very, very long time ago. I think more than 30 years ago, when I was working as a research assistant for another university. Last time, some professor working in the University of Okinawa invited me to give my series of lecture on my mathematics for his students. And he brought me to some restaurant for dinner. And we are waiting for dishes, so we ordered. Then he said, just suppose there are two glasses on the table. Of course, there were two glasses on table, actually, just for our beers. And he said, we want to compare the shape of these glasses. How? Suppose there are enough many beans, right? Take them and put them into the glasses, as many as possible, right? And count the number of beans put in each of these grasses. If they have the same shape and the same size, then the number of beans also will be same, right? Conversely, if the number of beans are same, can we conclude that they have the same shape? Of course, the answer is negative in general. Well, now we prepare the very small beans, like sesame seeds, okay? So then the number of such small beans will be proportional to the volume of the grass. So the number of such small beans might distinguish the size of the grasses. Conversely, if you use in a big beans like olive or oranges, what can we say? For example, the red grass in the picture, right? And that in a big, and maybe the answer will be able to accept one orange, but blue grass cannot. These arguments lead us to very interesting mathematical problems. Okay, suppose the number of beans of any size are equal, right? Then can we conclude that they have the same shape? Mathematically, it is the same thing that we consider the function of x that counts the number of beans of size x and compare some functions. We call such function the beans function. More generally, we can formulate this notion for matrix space. Metric space is just a technical term in mathematics, so you may consider it just a space or area where the distance of any points can be measured. Now this big rectangle represents a metric space X, and we try to put the points inside X as many as possible, so that any pair of these points have a distance at least X, like that. We denote the maximum number of such points in X by Bxx, right? This is a beans function of metric space X. However, this formulation is slightly different from that for grass and the beans. Of course, a large X, matrix X, play the role of grass. More precise speaking, I think it's the inside of grass. And what is bean? Now, I want to call each point presented as a small dot a bean. But you might want to call a yellow circle, yeah, right? Yellow circle a bean. The radius of your bean is the half of x. On the other hand, my bean is just a point and has no size, radius 0. So we can put such point at any place closer to the boundary of x. But if we use the yellow circle as beans, we need to solve delicate arguments near around the boundary of x. So I will consider only the configuration of points and the distance among them hereafter, right? However, I am a graph theorist, so I want to focus on the graph. The graph is a one-dimensional figure consisting of points and lines. While graph is a mathematical model for electric circuits and computer network and so on. And engineering side people call each vertex a node and each line a branch. But mathematicians, including me, call a vertex and an edge, just mimicking the naming of the parts of a polyhedron. However, now we should distinguish the vertex and the point when we discuss the beans function of a graph. In this picture, a black dot, slightly big black dots, are vertices. And each edge joining them is assumed to be in line segments of length 1. When I say a bean on a point, it is not only a point placed at the vertex, but also any point placed at any place along any edge, like this blue dot in this picture. Okay? And then the distance between the 2 points is defined as the length of the shortest path joining them. In this picture, the distance between 2 blue dots is 2.7 or 2.8. Because the blue broken line goes along 2 edges or more, but less than 3 edges. And such setting, we consider the Bean's function Bgx of a graph G. Then the value of Bgx is equal to the maximum number of points placed on the graph G, so that any pair of points have distance at least x. Make sense? To understand it more concretely, I will show you easy examples. Now we have a cycle. Okay, cycle. This picture will just show you a hexagon, but I guess you can understand it's a more general situation. This is a cycle. Suppose we have a cycle denoted by Cn, consisting of n edge. Okay, and try to put the points as many as possible, so that they have a distance at least x, right? And then it is enough to place the points at equal interval of length x. And we can put n over x points, right? N over x, n divided x, right? But n over x is not integer in general, so we need to round it down to the nearest integer. The symbol of this symbol is called the floor, and round down the value of its inside into the integer, right? If x is bigger than n, then the value of the round down is equal to 0. However, we can always put at least 1 point, so we should take the bigger one from 2 inside the brackets. Similar arguments work for the person of length n. Yes, shown in below. And but it has 2 ends, so we can put 1 more point. Now I will show you more complicated example. And the heptagonal figure presents a complete graph over 7 vertices, and that has 7 vertices and all edges between them. Any pair of vertices are joined completely by edges, so this graph is called complete graph K7. All right, so you understand what is a Kn, the complete graph over n vertices. But I'm not going to explain anymore about this slide. I want just to give you an impression of the difficulty in determining the Bean's function of graph in general. Okay? Also, I'm not going to explain the details of this slide. However, I want to emphasize the fact that the Bean's function does not determine the shape of graph in general. These 2 pictures show the example of the 2 non-isomorphic graphs that have the same Bean's function. They have the different shapes as you look, but their Bean's function are completely same. Therefore, the answer to the first question we discussed at the beginning of my talk is negative for graphs in general. However, we have found only example of lower connectivity like this. So I keep thinking about those graphs that their Bean's function determines their own shape. The complete graph is one of such kinds of graphs. Well, this is just my mathematical interest, but I have a very wide perspective about Bean's function as follows. This is a graph of Bean's function, but this is not the Bean's function of a graph, right? This is the graph over Bean's function of a graph, right? Understand? The graph of function this is, right? So since the Bean's function takes only natural number as its value for each positive number x, so its graph is not continuous and looks like a step function, which consists of many horizontal line segments. Of course, the Bean's function is this decreasing function, and that is when x is becomes bigger, then the volume of the function becomes smaller, and the graph goes down. To determine the Bean's function, we need to decide the height of these steps of dividing points along the x-axis. However, there are infinitely many steps, many lines, right? So how can we control them? To control them, we have already established a very nice formula. This is our formula proved by me and one of my students. His name is Kengo Enami. To understand the meaning of this formula, we should divide the x-axis by unit fraction. Unit fraction is a fraction of the form 1 over n, right? That is 1 and 1/2 and 1/3 and 1/4 and so on. And consider the translation x into x over 1 plus x. This translation shifts each interval bounded by the consecutive unit fraction to its left one, right? For example, the yellow area is moved onto the blue area. According to our formula, we must shrink the width of this area and rise up the graph part by the number of edges. Conversely, move back to the right one by one, and then we finally reach the orange area, right? That is interval between 1/2 to and 1, right? And this means that if we can determine the Bean's function only over this interval, we can know the whole of Bean's function over all orange. Make sense? Orange interval determines all range. Just kidding, sorry. Today, I'm not going to explain more details, but it is important that we can determine the whole Bean's function, just combinatorics on arrangements of small number of Beans, okay? I will stop the mathematical arguments now and touch on the topics on the application. Social distance along the streets in the city. As you know, the network of streets or road in a town or a city can be expressed by the graph with its vertices and edges. Of course, each edge corresponds to the street, and the vertex corresponds to the crossing of streets, right? My question is, how many people can stand in this city keeping social distance, right? Usually, the social distance is 1 meter or 2 meters. It depends on the government's decision against the coronavirus infection. However, if we have the Bean's function of this city, we can answer to this question immediately for any decision of government. Here you should recall that each edge of my graph has a unit length 1. Therefore, they are supposed to have the same length, but the street in the real city will have the different lengths in general. In such a case, it is enough to consider the network subdivided by the suitable small unit lengths, or as in the picture. Well, I have no idea, no more than this to say about the application of the Bean's function, so sorry. If you want to know more about beans functional graphs, please come to Yokohama National University and join us. Discuss together to get new ideas and create new research. That's all. Thank you for your attention. This is Seiya Negami from Yokohama National University in Japan.
Okay. Thank you very much for Professor Seiya Negami from Yokohama National University, Japan. Okay, for this wonderful presentation. That's how the mathematician make a difficult thing to become easy to understand and interesting. Thank you very much, Dr. Seiya Negami. And the next speaker is the Professor Dr. Benyamas Serslip from Prince of Songkla University, Hat Hai, Thailand. She will speak about industrial biotechnology. Please give warm welcome to Prof. Benyamin Serslip. Prof, you have about 20 minutes for presentation. Please, the stage is yours. Okay, we're waiting for her.
We can just discuss about the two topics first. Prof?
Okay, thank you. Okay, there's some technical problem. So now we will have a time for question and answer for the two topics from Dr. Ariel and Dr. Seiya Negami. Please, if from the committee, they have already some chat coming in for the question. Let's see. Oh. If anyone have any question, please raise your hand and for Dr. Ariel and Dr. Prof. Seiya. Okay. Okay, if not, I have question for Dr. Ariel regarding the net zero in your university campus. I would like to ask what the percentage of the biomass contribution for the energy supply for the university. Okay. I think we in University of Samratulangi, we start already to recycle the leaves from the campus and to produce something product compost from that biomass. But I would like in case of the Monash University, what looks like the role of the biomass for the energy supply in the university. For Dr. Ariel Lippman, please. Thank you.
Okay, Prof. Julius Panto. The questions for Dr. Ariel Lippman will be collected because Dr. Ariel Lippman has got another commitment right now. So he will sure answer all the questions that will be addressed to him, but for now, he's not available. And we are waiting for the next speaker, which is the Professor Benyamas Serslip. And because she is scheduled to talk at 10:30, And she's now still in a meeting and we are waiting for her. And unfortunately, Professor Seya Negami Chu is only giving video presentation. So what we can do right now, we can collect all the questions for those two speakers, and then we will direct the questions to them by email or by WhatsApp. That's all we can do for now, Professor Julius.
Okay, Dr. Menteri, could we not just put in the chat and we will address it later on to the two speakers?
Yes, yeah. Participants can write down the questions in the chat. Host, please make chat available for all participants now. And make the chat to be seen on the screen so everyone can see it.
Okay, thank you. So, Dr. Menteri, they have information how long we have to wait for the Prof. Benyamas.
Professor Chersil will be available at 10:30. It's about 10 to 11 minutes from now.
Okay.
So actually we have a question for Dr. Ariel Lipman from Profesor Inengya Suparte, Dekan dari Dekan
Dr. Prasad
of FMIPA.
Dr. Prasad has joined, so maybe you can ask if
okay.
Can do the talk.
Okay.
Okay.
Good morning, Dr. Prasad.
Morning, morning.
Welcome, Prasad. How are you?
Good. Thank you.
Oh, good. How's Brisbane?
Well, everything is under control here. Not that bad. We don't have any more cases of COVID.
Oh, that's good. It's nice seeing you again. Okay.
And it's good. Yeah.
Actually, we are waiting for Professor Benjamin Chersil because she's still in a meeting and she will be talking at 10:30. And what we are thinking is if you are ready now, we can probably let you go in first.
Yeah.
Present your presentation yourself.
Yeah, sure.
Will it be possible?
Yes, no problem.
Okay. Professor Julius, it's all yours now.
Okay. Thank you very much, Dr. Vicky. Now the next speaker is Professor Dr. Prasad Kapayu from Griffith University, Brisbane, Australia. He will present about the biotechnology. So please welcome Dr. Prasad Kapayu. The stage
Thank
is...
you. Thank you, Julius. So should I just share my, 1 second, I'll share screen. Right, is it good? Can you see my screen?
Yes.
Yes, perfect.
Yeah, okay. Thank you, everyone. Thank you, Chairman, for the invitation. And I'm very glad to be here. And today I would like to talk about some of the applications of environmental biotechnology to actually produce renewable fuels and also renewable chemicals. Now, my topic today is about the biogas production from agriculture, or energy crops and agricultural residues. Now, if you see that that most of the time, the transport sector is considered as one of the major sources of greenhouse gas emissions. And after energy and of course, after the agriculture. So we are trying to see that if the agriculture is self-sufficient in producing energy, especially renewable energy, and in the form of biofuel, then it can actually substitute the amount of fossil fuels that are actually required and also reduce their own energy needs in the process heat and energy requirements. So in Australia, we see that agriculture accounts for about 16% of the total greenhouse gas emissions. And we consider it as a major source and sink for greenhouse gas emissions also. And the intensive farming has actually led to the increase in the energy demand, and especially the irrigated crops. And one of the major crop in Australia is the sugarcane. So sugarcane is a very intensive agriculture crop. So we are trying to look if we can replace the amount of fossil fuel energy that is required by using its own residues coming from sugar mill or coming from the agriculture. We can actually take care of their own energy needs. Now, the technology that we are using is basically the anaerobic digestion technology. So this is a kind of a well-known microbiological process where microorganisms are actually used to degrade the organic matter and produce biogas. Now, the biogas is a mixture of methane. The concentration can be about 50 to 70% methane, and then also carbon dioxide, which is around 30 to 50%. Now, this is being considered as a carbon dioxide neutral because the produced carbon dioxide on the combustion of the methane can be uptaken by the new growing crops. Now, the produced biogas can be used for producing electricity, or in a cogeneration plant, we can also produce both heat and electricity. Nowadays, we are also looking at how we can actually improve and utilize the biogas for reducing the transport greenhouse gas emissions. So we are utilizing the biogas to upgrade the biogas and use it as a bio-CNG. Now, globally, we see that there are more than 40,000 biogas plants in the world, and almost 50% of them are in Germany. And then you will see that the total installed capacity of biogas plants in the world is about 1.3 hexajoules. So that means 10 to the power of 15 joules. And Germany, United Kingdom, and Italy are the major contributors of the biogas industry. Now, as I said, that we can use the biogas for producing heat alone, or heat and electricity in combined heat and power plants. And also nowadays, we are looking at using the biogas for vehicle fuel. So basically, you can replace the petrol engine as a substitute. So what are the feedstocks that we are interested in then? Any organic matter, right? It can be from food waste from your homes to the garden waste, or you can also use grow specifically some energy crops like maize or sweet sorghum, and then use them as a feedstock. Of course, you can also use the organic fraction of the municipal solid waste and then also sludges. So all those what I have highlighted are the major feedstocks like agriculture manures, slurries from farms, crop residues, and sewage sludges. Now, these wastes can be used as a commercial source for biogas production. Now, here I have put a table showing you the different feedstocks and their biogas potential, and how many passenger cars can be driven if you have 1 hectare of that crop, right? So, for example, maize is considered as a major feedstock for biogas production because it has a very high biomass yield And as you can see that it's about 20 to 30 tons of dry matter per hectare. And it also has a very high biogas yields. Now, if you use the biomass that is produced from 1 hectare, you can actually drive 7 to 10 passenger cars about 10,000 kilometers per annum. So that's the range of biogas you can actually are replacing the petrol when you use the biogas in your vehicles. So these are some of the major crops, and you can see at the bottom, I have sugarcane, bagasse, and thrash. So we will talk about that later because that is what I'm now currently working on. So I have worked on all those crops which are shown here, and we are actually trying to develop technologies in Australia where we can actually use the sugarcane residues like sugarcane bagasse and sugarcane thrash, and also grow sweet sorghum or energy cane. I mean, that means that you are just growing sugarcane specifically for producing biogas. Now, what's the concept then? So what I'm showing here is the farm scale biogas plant concept. So you can see that this is a farm where they are basically growing agriculture crops. You can see at the bottom, let's say some crop like maize. And then that maize is actually used as a source of feedstock for biogas production. You can also combine with other materials coming on the farm, like livestock manure, and then you can co-digest these two together in the biogas plant. Now, the produced biogas then can be converted into heat and electricity using your combined heat and power plant. Now, this can be from 50 kilowatts to very big units like 250 kilowatts. Now, the heat can be fed into your own factories or industries for your on-site heat requirements, or they can also be used in the greenhouse gases to heat up the greenhouse gases, or also for space heating in the residential sector. Now, the electricity can then be fed into the grid. Now, most of the plants in Germany, they are actually interested in that aspect of feeding the electricity to the grid. So you get a feed-in tariff about 6 to 8 euro cents per kilowatt hour that you are feeding into the grid. So if you imagine the fossil fuel electricity in Germany is around 6 cents per kilowatt hour, whereas the renewable electricity that is coming from biogas is sold at maybe 14 to 17 euro cents. So they are basically having a good revenue when they are actually using their own biogas for producing electricity. Now, the first energy crops that I should talk today is about maize. Okay, so we will see how maize can be used as a biogas production. And so we try to screen different varieties of maize. Now, normally in a food grain production, like if you want to produce maize for kernels for edible purpose, you are actually looking at a very short varieties, and we have very 3 to 4 crops per plant like that. So these are the traits that you are looking at from the food production point of view. But for a biogas point of view, what we call as energy crops, we want that there's a high biomass yield. So it should be around 20 to 30 tons per hectare of biomass. So that would be the ideal to get a high biogas productivity from per hectare. So we harvest these different strains. So we are screening different varieties of maize, and then we try to produce biogas. So this is in a lab where we can actually produce biogas testing. Now you can see here all the 8 varieties that we have tested. We have some varieties that have yielded very high. And then some varieties have very low biogas production. So we try to understand what's the biomass characteristics and how biogas yields can be improved by using different techniques and optimize the biogas production. Now the last variety, Waldech, has the lowest biogas yield, and whereas they are followed by Ronaldinho. And then we have these 2 very important varieties that we screened further to see how we can actually store, because you can see that the biogas production has to be a continuous year-round production, right? But the agriculture crops are only seasonal, like you only grow for 3 months and then you are harvesting that. So you need to store this large amount of biomass on field or on the fields, so that you can feed your biogas plant on a regular basis throughout the year. So we took these couple of varieties and tried to understand if we can store them by ensilation process. Now, ensilation process is where you are basically same thing as pickling, what we call, like, if you go to a supermarket, you buy cucumber or gherkins in a pickle, like in a salt water or brine solution. They stay for many, many months. So same thing, we are using lactic acid as a source of decreasing the pH of this biomass, and thereby killing all those other unwanted microorganisms that can actually spoil your biomass. So we can see that most of the plants have some losses during the storage, and that can range from 2 to 4%, but some varieties have the highest biomass losses. But the most important thing is that we are actually preserving the biomass so that we can use for a year-round application of as a feedstock for biogas production. And then we try to understand if there is an ensilation process actually improves the methane production or not. And we have studied 2 best varieties. We continued and we saw that the methane production was much, much better than the untreated materials when you do an ensilation process. So then we actually try to take the best variety and the worst variety of the maize varieties, and then try to do another high temperature pretreatment, and also see if they actually improve the biogas plant. So once you have grown those plants, now we want to scale up to a farm scale scenario, a real farm where you can actually have the maize varieties growing, and then you can actually use the biomass for biogas production. And here is the farm where you can see that this farm has about 70 hectares of agricultural land, and there are about 40 cows in the barn here. This is the house where they are milk, the dairy farm. So this is basically has 40 cows. And the cows produce about 2,000 cubic meters of manure per annum. And that is stored in this pre-storage tank. Now, what you're seeing here is the biogas plant. And this biogas plant is about 150 cubic meters. So we are feeding the biogas, the energy crops that are grown here on the farm, and also the manure that is produced from the farm, and then try to produce biogas. Now the gas is then fed to a combined heat and power plant. It's a 50 watt CHP plant. And then the electricity that is produced is used for the milk station in the barn, and also for the farm own needs, and also fed to the grid. Now the digested material that comes from the biogas process is then stored in this post-storage tank. Now why we are storing? So this is one of the most important thing in a farm scale, is that all the nutrients in the biomass are conserved during a biogas process. So that means that your nitrogen, your phosphorus, and your potassium, they are not lost during the biogas process. A little, maybe less than 3% of nitrogen is used by the microbes, and about 50% of carbon in the biomass is actually converted to biogas. So this is how we are actually trying to show the farmers that biogas process is considered as a sustainable way of not only for the waste management, but also for renewable energy generation, and also nutrient recycle, especially in a closed cycle of carbon and nitrogen in a farm scenario. So we apply the digestate on the farms and try to grow the energy crops again. So then we have also feeding the biogas to a biogas upgrading unit here, okay? And that gas can be used as a vehicle fuel. You can see here a car fuel, and I have much better. So this is the technology that we have developed, is the high pressure water scrubbing technology. So we use the water as a medium where we can all absorb the carbon dioxide and hydrogen sulfide and other organic compounds which are not required or which are very bad for the combustion of the gas engines. So we will try to remove everything so that we get a pure methane of 96 to 98%. Now that methane is compressed to 200 bars, and then we store that in a gas bottle. So on the background, you can see here the green bottles are the compressed gas is then stored. So here is the process drawing technology, where you can see that the raw biogas is fed into a kind of absorber columns. And here we are feeding the gas from the bottom of the column, and then water is fed from the top. As the water is filling, this gas will have no other ways to go, but the pressure is increasing in the absorber column. And as the pressure is increasing, and then you will see that all the contaminants like carbon dioxide, hydrogen sulfide, other volatile organic compounds are actually absorbed into the water. And then the pure methane is then fed into a dehumidifier, and then it is removed the humid conditions and then send it to the gas filling stations. And then the water, which is now absorbed with carbon dioxide, is then sent to a kind of a flash tank where we will release the pressure, and then all the carbon dioxide and other compounds will be released. And then we can recycle the water back to the absorbing columns. Now you can see here the purity. So you can compare the raw biogas characteristics. So before the biogas is upgraded, you see the biogas methane content is around 50% to 62%. And the carbon dioxide is about 38 to 45%. And the H2S is around 300 to 500 ppm. Now you had to basically remove carbon dioxide, hydrogen sulfide, and also all the other organic compounds.
Dr. Pasado, you have 4 minutes.
So, sorry?
You have 4 minutes more.
Yeah, thanks. And then we have the biomethane concentration here. Now the vehicle fuel standard says that you must have minimum of 96% methane, and that's what we are trying to achieve. We're also looking at so that's basically a car that is being filled with the filling station, and we are also looking at the upgrading use of biogas in tractors on the farm. Now coming to in agriculture in Australia, yes, you can see that sugarcane bagasse and thrash are considered as the major agricultural residue. And we are trying to, in this project, we try to show that sugar mills can be sustained if they can actually replace their own, utilize their own sugarcane bagasse or thrash and produce biogas. So we have tried different pre-treatments to improve the biogas production. And also we have tried to see that, demonstrate that we can actually produce this biogas in a pilot scale biogas plant in a sugar mill. So this is my pilot scale biogas plant. There are like 4 biogas reactors. At the background is the biogas upgrading unit. And here is the compressor. And then those are the gas bottles where the compressed natural gas is filled. And we have tested them, and we were successful to produce high purity methane. So here, for instance, it's 89% methane and 5.9% carbon dioxide. Hello. And you can see at one point we reached 96% methane. So our calculations show that if we actually take not so much, maybe on the 15 to 18% of sugarcane bagasse from a middle-sized sugar mill, we can actually replace their own fossil fuel requirements, because the diesel consumption for sugarcane cultivation is roughly around 500 liters per ton of sugarcane that is produced. So that is coming to be a very expensive for the mills, because they are not only spending a lot of fossil fuel energy for irrigation, but also for the transport of the cane from the farm to the mills. So we are trying to replace the diesel with to produce biogas. So that's what my presentation is about. So if you have any questions, please ask me.
Okay, thank you very much for the very interesting presentation, Dr. Kaparaju. And now we give for the participant to ask questions. If you have, please raise your hand and let us know. Here they have question in the chat. Oh yeah. First from me. Yeah. Do you have any? You already mentioned about the biomass potential of the sugarcane. Yeah? Is about 30 to 50 tons per hectare. Yeah? That's right. And that's just, but that's just for the what they call it? Baggage. Yeah.
Yeah.
Just the baggage. How about for the total, including the sugar and the trash? How much?
So if you take whole cane as such, right? So you get more than 380 cubic meter.
380 cubic meter, yeah?
Yeah, per kg of material.
But kg cubic, you means?
Sorry?
380
cubic meters of biogas.
Cubic meter biogas.
Yeah.
But in terms of the weight of the biomass itself?
What
tons? What in terms of tons?
In Australia, we get about 100 tons of cane per hectare, 100 to 120.
100 to 120, yeah?
Yeah.
A ton per hectare, yeah? And that's for how long? For 12 months or 14 months?
This is a 6 months crop.
Only 6 months?
Yeah.
The sugar can be harvested only 6 months, or?
Yes, only 6 months. Yeah.
Oh, okay. So if consider the biogas, the biomass production, sugarcane is the best, is the highest plant crops can produce biomass. That's right.
Yeah, if you take whole biomass.
Yes.
Yeah, of course, because you have a lot of sugars, and sugars are much easier to be converted to biofuels, either whether it's ethanol or biogas.
Because I'm comparing with the biomass production from the palm sugar.
Yeah.
Because palm sugar can produce, according to our calculation, about 50 tons sugar. 50 tons sugar per hectares per year.
Okay. Yeah.
But the other biomass is not much. You know, maybe about 10 tons. So total is about 60 tons. So it's still lower to compare the sugarcane, eh?
Yeah, sugarcane is the highest if you take it as a what you call sugar content. Yeah.
Oh really? Oh, okay.
Yeah. So for example, we produce about we have 360 hectares of sugarcane area.
Yeah.
We produce about 4.3 million tons of sugar.
4.5 million tons.
4.3 million tons of sugar from 360,000 hectares. So if you calculate, you will know how much we are producing per ton.
because I was writing a paper about the comparing the biomass production of the several crop and plants, and I found that sugar plant sugarcane is quite high, but also we know the in terms of the sugar production, the palm sugar is the highest because can produce up to 50 ton sugar per hectare per year.
Yeah. So yeah, in terms of because bagasse and thrash, the bagasse accounts like 30% of cane, right? And then thrash accounts around 19 to 20% of the cane weight.
Yeah, but the sugar I know just about 14 tons per hectare per year. In Indonesia, we produce about, that's the highest, about 14 tons per hectare per year.
Yeah.
So not
here we have 100 to 120 tons per hectare of cane.
Okay. Yeah, that's a little bit confused about that. You know.
It's a lot. It's a lot. Yeah, it's a lot.
I surprised it's quite a lot. You know.
Yeah.
Okay. So, but I will go through that. Okay. Thank you very much. And the second question is in terms of the conversion of the biomass by methane production compared to the like sugar. For example, we take sugar, not any biomass. We take sugar to convert by yeast
to biogas,
and biogas. Which one the better, or how much the percentage?
If you take sugar, because now, to be honest, I don't know whether we can say that, but most of the sugar mills are not so profitable because the sugar that is coming into international market, they are basically coming from India and Thailand. And so these are like, you know, much cheaper compared to Australian sugar. Okay. So the sugar mills are not able to make any profits out of it. So they are thinking that should we use the sugar as a feedstock to produce biofuels. Okay. Now, because sugar is basically glucose, so you can actually produce about 420 cubic meters per kg of sugar. 400 cubic meters per ton of sugar. Okay. Using sugar as just feedstock for biogas production.
Biogas, yeah. But if did you any make calculation go by the fermentation by yeast?
Yes.
How much?
Yeah. That's what I'm. If I do fermentation, I will get around, for example, 400 to 420 cubic.
Yeah. And by the methane.
No, I'm talking about methane, right?
Oh, you're talking about methane, yeah.
Yeah.
But by fermentation by yeast, no, you don't have.
Okay, ethanol. You mean ethanol? Yeah. If you have one glucose of, you will get for every gram of glucose, you get 0.5 grams of ethanol. Almost 59%.
Okay.
Okay.
So that is.
Okay, sorry.
So every gram of glucose you use for ethanol production, you produce
about
9 grams of ethanol.
Yes, that's right. Yeah.
Okay. Excuse me, Prof. Leus, maybe we should take questions from the participants right now. In the chat room here, I've got 2 questions written down by the participant.
Okay, please.
Directed to Prasad.
Yes.
The first one is, in your biogas production, which is anaerobic digestion process, does it utilize syntropy mechanism run by specific microorganisms? That's the first question. Did you get it? Okay.
Yes, I got it.
The second question is in fermentation of plant into biogas using natural microbial from animal. So probably the question is, do you use animal derived microbial for your biogas production?
Yes.
Yeah.
Okay. So the first question is, I think these are two interesting questions. So the first question is that what was the, are we converting this microbes, right? Talking about microbes.
Mechanism.
Yeah, syntropic.
Yeah.
So the microbiology, if you, can we put the slide again or?
Yes, yes, please. You can share it again.
Yeah, can you see?
Yes.
So what you're seeing now is basically the bioprocess, the biochemical chemistry of the biogas process. So as you see on the top is the organic matter. And that organic matter has to be degraded in a cascade of 4 different main steps. And this is facilitated by 4 major groups of microbes. The first one is the hydrolysis, we call it, where the carbohydrates, proteins, and lipids are hydrolyzed to simple compounds like sugars, amino acids, and long-chain fatty acids. And this is done by hydrolytic bacteria, like Clostridium, for instance, if that is very common species, but everyone knows. And then the next step is the acidogenesis. So these monomers are then converted into organic acids and alcohol and hydrogen. And that is also done by the same group of microbes, which are doing the hydrolysis, and they actually carry out this in the form of a fermentation. That is what we are seeing in a ethanol fermentation also. Third group of bacteria, we call it as acetogenic bacteria. So they utilize the organic acids like acetic acid, propionic acid, butyric acid, and also alcohols, and convert to acetic acid, hydrogen, and carbon dioxide. Now, these actually have the syntropic association relationship with the methane-producing bacteria, which are at the bottom of this hierarchy. The last step is the methanogenesis, where these are the primitive archaea, which utilize the acetic acid or hydrogen and carbon dioxide to produce methane. So they had to have a syntropic relationship with the acetic acetic acid forming bacteria. Okay, so that's the relation. So between stage 3 and 4, you will have the syntropic relationship. Now coming to the second question, whether we are using the microbes. So this is a mixed culture bacteria, what we are using for producing biogas. For ethanol, you are using yeast, and that's basically a mono microorganisms. But here, we use the mixed culture. As you can see, that we need all these 4 different groups, and they had to work together and transport the protons across, or electrons across these microbes. And we can take anything. So because all ruminants, including us, we also have different groups of microbes in our system. So this is a natural process where what's happening in the stomach of a cow or any other ruminants will actually have all these 4 different steps of hydrolysis, acetogenesis and methanogenesis. So the same thing happens. So, but when we take, for example, if you take a manure from a cow and try to produce biogas, so the proportion maybe is not that good. So you are always taking from an existing biogas plant, which is running very well, as a source of inoculum to start your own reactors. But basically, all ruminants will have the required bacteria to start this process.
Okay. We've got a third question here from the participant. It's from Johannes Mandi. The question is, would you please share if you have the life cycle analysis of the biofuel process of yours from cradle to grave? That's the question.
Not now, but if you give my email, I can send. Okay, so yeah, so because life cycle analysis shows that among the different fuels that we are producing, biogas is considered as one of the best. Okay, because our starting material is waste.
Okay.
Yeah, the waste. So we are not actually putting so much energy. So if you put 1 megajoule of energy into the system, you are producing around 1.8 megajoules of energy out. So, or times, sorry, 1.8 times the energy out. So it's considered as more sustainable after bioethanol from sugarcane juice in Brazil.
Okay, so thank you very much, Prasad. Back to you, Prof. Julius. Yeah.
Okay. Okay, thank you very much, Dr. Kaparaju, for the very interesting. I always interest to this kind of the work. Okay, because I'm also with the how to produce ethanol from sugar palm.
Yes, yes, yeah. So there's also integration of those two processes can be also done. So for example, one of my PhD students, she's looking at first producing ethanol from sweet sorghum, and the residues from the ethanol plant like stillage is used as a raw material for biogas process.
Okay.
The integrated process.
Okay, thank you very much. It's very
Thank you very much. See
you.
Bye.
Bye-bye. So next, can we continue for the committee? Can we continue for the next speaker? Dr. Vicky Mantiri is Prof.
Sound.
Okay. Yes, thank you very much, Prof. Leos.
Okay. Please.
Okay. Hello, everyone. My name is Vicky Mantiri, and I will be the moderator for the next 2 speakers. In our list of plenary speakers, the next speaker is Professor Dr. Muhammad Basharuddin A. Rahman from University Putra, Malaysia, Selangor, Malaysia. And today, Prof. Rahman will deliver a presentation entitled Embracing Molecular Simulation Solutions in Sustainable Biocatalysis. But before we get started, I would like to go over a few items so you know how to participate in this plenary session. This online conference is being recorded and is streamed live on YouTube. We will be able to share a link with you after the event is complete. We welcome you to revisit the content yourself and share it with your colleagues. The 2 presenters will deliver their talk for 20 minutes successfully. This will then be followed by 30 minutes Q&A time. Participants will have the opportunity to submit text questions to today's presenters by typing your questions into the chat pane. Please write down your question and to whom your question is addressed to. And then later on, the host will choose the questions that will be discussed during the Q&A session. So, ladies and gentlemen, without further ado, please join me to welcome Professor Muhammad Basharuddin Rahman. Prof. Basharuddin, the floor is yours.
Okay, thank you very much, Professor Vicky, the chairman. And again, I would like to say Assalamualaikum, good morning, and selamat pagi, selamat tengah hari ya, to the participants, to all. So I am very glad that being contacted by the Professor Benny. And I would love to share some of my works that are related to the molecular simulation, particularly for sustainable biocatalysis. Right. Okay, so here are some of the fundamental issues that we normally discuss in the Sustainable Development Goal, where how we like to see the focus of the science and at the same time to remain most of the sustainable development. And for example, in our work, we are not limiting to particularly one SDG, but if you also discuss about the IoT, the Internet of Things, which is actually one of the most talked about, we can see that there are many what you call this overlapping between the SDG and the IoT. In particular, in our work, number 1, 2, 3, 6, 7, 8, 9, 11, 12, 13, 14, and 15. Yeah. So as I think in Southeast Asia, like Malaysia and also Indonesia and Thailand, one of our major work is actually related to palm oil. This is what I'm going to discuss a little bit more on that part. The most important when we look at, by the way, I'm a chemist, so the perspective is still as a chemist, but then we look at the biology, particularly on the system biology. So we move from structural and then to systems biology to understand what we can find out from, for example, from the genome, the system. Then we also work out with the technology people, or basically the engineers, particularly to address some of the fundamental questions. But for example, in terms of to do the scaling up, that leads to some of the practical innovation. And of course, at the moment, most of our works right now is heavily being carried out in terms of the computational. And when most of the universities or most of the countries being locked down, somehow computational is the only one that right now making throughout the lockdown process, where the what you call this, the experiment can be carried out compared to the lab work. So in this work, some of what we've done is actually also through the theoretical exploration. This is actually more like I would like to share through our computational work, particularly computational biology. So as I said just now, when we talk about the bio-based research in biocatalysis, so one of our focus is actually on the enzyme, and we are working in different part of bioprocess. Of course, we know that if you want to do the better enzyme, we know that enzyme is very fragile. We do a lot of kind of improvement, either through rational design or directed evolution. We also do some substrate engineering, and some we also work on the immobilization. Some of the work that I will present here also involved in immobilization, and other than that is of course the chemical reaction. But to do it through traditional way, I believe it's going to be very difficult right now. So that's why we move into the structural, computational, and I think right now people start to focus more on the chemical biology, so that we can leverage the usage of the computer simulation, because from here we basically understand how basically the mechanism, for example, yeah, and we can use in many different application. Particularly right now, the talk is more on the biomedical, for example, COVID-19. All right. This is what we have carried out, or the focus in the beginning, where we want to produce more of the products from our palm oil. So that's why I said just now, like in Indonesia and as well Thailand, we are working on this. Here's some of the product, but of course there are many limitations. For example, the catalyst itself, the process engineering itself. Yeah, so that's why from here, for example, when we have our palm oil ester, so we move into the computational colloids, where we study more on the nano emulsion. Yeah, for example, this is actually one of our first paper in 2008 or 2009, where we studied how can we get the correct, or our formulation can be very much related to the theoretical value that proposed by Davis way back in 1994. And through our computational calculation, we've been able to show that the size, shape, and the structure of my cell is actually related to the one that been predicted. And from there, we expanded the usage of this computational colloid in order to study a drug delivery, and currently we are more on the transdermal, parenteral, and pulmonary delivery. Yeah, so this is actually very interesting. For example, when we studied the usage of ibuprofen, we can see that the ibuprofen basically stay intact at the layer. So that's why we can claim some of our works that it is actually fast release, and some of the drugs that we use is actually embedded slightly inside into the core, and we found that from the experimental work that it is actually a slow release. So this is actually very important when we want to work either for the biomedical application or for agriculture application, if you want to control release your fungicide, for example. So this is actually one of our major focus. And recently we work more on, this is actually the overview. We are not limiting to a pharmaceutical. And I think I mentioned as well that we also use our palm oil ester that we derive from our enzymatic process, then make it into formulation. So in certain like cosmeceutical, which is actually more on the topical application. Then for agriculture, basically for the pesticide, we're working on the fungicide and also pesticide, and some of the pharmaceutical. Yeah. And currently we are working on the aerosol and lung cancer in collaboration with Harvard School of Public Health. And from here, it is also very interesting that how we being able to control the size of the nano emulsion from, for example, in this work here, from 100, 150, and 200 nanometer. And we can also show the different toxicity where the smaller the size of the nanoparticle is actually giving a more nanotoxicity environment. And this is actually very important because in order for, there are many claims that nano drug is actually better than the normal one. But again, we need to study in detail about the size. The size of each nano formulation or nanoparticle drug definitely give different nanotoxicity. So something that we need to control. And other than that, we can also show that the drugs, basically, this is, how to say this? This is actually from next generation impactor, where we want to see where does the drug deposited in our system. So from the nebulizer, we found that it is actually more on the stage 4, 5, and 6, which is actually representing the alveoli, and the bronchus. So it is very important. And this application, for example, can be used also to for the COVID-19 because of the inflammation in the lungs. So we are actually right now start to try to formulate something, formulation to reduce the inflammation of COVID-19. Yeah. Other than that, of course, we need to do the scale up of our nano formulation, as can be shown from here, some of the RSM. Yeah. So furthermore, other than that, I think this is interesting. Other than focusing just on the nano emulsion, yeah, basically as a liquid, but we also focusing on the materials, where all the nanomaterial, for example, the graphene base, mesoporous silica, nanoparticle, iron oxide, and also MOF, which is actually the metal organic framework. So from here, we have developed, this is one of our latest work, where once we, in collaboration with the University of California, Berkeley. So when we managed to synthesize the ZIF-8, but then we change, or we make into an alternative green chemistry, where we synthesize it at room temperature and in water, we being able to reproduce the ZIF with the controlled size. And from here, we what you call this? We encapsulate the drug inside the ZIF. Then we put the homing peptides. Basically, it's like a GPS so that it can track where it should bind to the cancer cell. And from here, it is very interesting to see that from the AFM, what you call this atomic force microscopy, we can show that the roughness of the surface actually playing a major role for the system or for the nanoparticle to enter or to penetrate the cell. And in this work, we started or we used zebrafish embryo to see the permeability, and we've been able to show that with the presence of the homing peptide and based on the roughness of the AFM, we can show that it being able to penetrate the cell, or in this case is actually the embryo. And same as well, we did more of the permeability and nanotoxicity study for this nanomaterial work. But since I would like to, other than that, this is actually one of our major work as well, where we did lots of immobilization of enzyme. So we've been able to show as well that the enzyme can be trapped inside the metal organic framework. However, the calculation or the simulation of CRL of Candida rugosa lipase in NanoZiv is actually still ongoing. But recently we have published one paper to look at what's going on inside of a metal organic framework. In this case, we work on the cutinase inside the MOF74, and the interesting part is actually to see where does the hydrophobic and hydrophobic surface activity that interacted between the enzyme and as well the wall, the inside wall of the what you call this, the MOF74. It is very interesting as well to see that how MOF74 being able to conserve the structure of the enzyme at a higher temperature. So it is actually very important when we work into enzymatic reaction, we can at least give to a higher reaction temperature up to maybe 70 to 80 degrees Celsius. And this is actually very good in order to get the higher activity. So that is actually more on the biocatalysis part, where we can be being able to produce higher activity and as well at the same time do the immobilization and of course some of the products. But we also still have a very focus or our interest in terms of designing a new biocatalyst, particularly artificial metalloenzyme, where we like to merge between these two worlds, the enzymatic catalysis and as well the metal catalysis. Yeah, because we know that there are many metal embedded in most of the enzyme. I think about 1/3 of enzyme basically contains metal. But now using computational and theoretical work, we've been able to create certain area, to synthesize a semi-synthetic enzyme that contain metal. But however, it is actually still very, very challenging task due to complexity. For example, the cofactor metal, basically metal, have a different calculation, and of course, furthermore, if we want to talk about the multi-scale approaches, it is actually again another advancement that we hope that we can work with a good system. Yeah. So we have several genome that we have complete its sequence. One of that is actually a Glycosoma antarctica genome, where we isolated it near the Casey station in Antarctica. So from there, it is actually interesting when we studied the metal contents inside this yeast. Actually, it's a yeast. Yeah. So we found that Of course, zinc is actually the highest, if you can look at here as well. But there is a traces of molybdenum, and the worst is actually tungsten, cadmium, mercury, and lead. Because when we start to study the seawater, particularly during the early atmosphere and the later atmosphere, which is actually the current, and the previous, like more maybe 100 or 200 years ago, basically during that time, there is no traces of tungsten, cadmium, mercury. And this is also an indicator that this is basically trapped the pollution or the heavy metal, or basically what we can say that the pollution is already entering the Antarctica area. So other than this, we also work on, so this is actually the metal ions distribution, particularly the zinc, magnesium, calcium, ferrum, and manganese between in each cell. So it have a different percentage either in the nucleus, Golgi apparatus, and so on. Yeah. So there is another interest as well that happened by accident when we start to study one particular antifreeze protein. So it is actually interesting how the organism or the microorganism adapt at minus 60 degrees Celsius in Antarctica. So they have one what they call as the antifreeze protein. During that time, we're not able to crystallize the protein. So end up we predict the structure, and based on the structure, we hypothesize that the antifreeze activity comes from the helical parts, and from there we synthesize all the 4 helical parts, and we determine the antifreeze activity, and we found out that it is actually as high or almost high as the parent peptides, parent protein. So from there we synthesize the antifreeze peptide, and then we study the structure and also the NMR structure, and we did some modification in order to make it stable. When we simulated it, the interaction between the peptides and the water molecule, or basically the ice, we found a very interesting information that leads us to do many application later on. For example, for the peptide 1M, we can see that the straightforwardness, meaning that all the side change of the amino acid interacted with the water molecules, but then the 4M slightly only maybe about 2/3, but for the peptide 3 only half, and it can be reflected as well from the experimental work, where 1M is actually the highest activity compared to the 4M and 3. So from here, we explore in terms of the cryopreservation. We also work on the food application, for example, in making ice cream that have a small or which do not have a large ice crystal, because to maintain the smoothness of the structure or the texture of the ice cream. So in this work, we've been able to use for the skin graft cryopreservation, where we can see that it is actually better compared to the common method that people use, glycerol, after 22nd day of post-translation, and it gives what you call these a good healing and less what you call these scarring into the skin. So currently we are working more into the organ transplant. I think this one is I'm working with a veterinarian. So we're talking about the collaboration. Other than that, in the rubber plantation, we also isolated one bacteria, which is actually the Bacillus lehensis. When we studied the genome, we found that there are many unknown structure or function, in particular what we call as the hypothetical proteins. And from there, we've been able to fish out several proteins, for example, the copper binding, SCO1 protein, the cytochrome, and metallo-beta-lactamase. And some of this work is being proceeded into antibiotic research. But now I would like to focus, I think the end of my talk, this is actually one of our focus area as well. Based on our success studying the antifreeze peptides from the antifreeze protein, we now have a know-how how to cut the protein into a smaller pieces, and it should be working as good as the parent protein. So we try to use a peptide that we mimic from certain part, or normally the active site of the protein or the enzyme, and we use it for chemical reaction. We focus more on the asymmetric reaction like aldol and Michael addition, and then as a transfer, and currently we're also working on the oxidation. We use aldoketoreductase, lipases, and ligases. We've been working with lipases how many years? Yeah, more than 15 years. And we thought that lipases would be the easiest one that we want to start with. But it turned out that this is one of the most difficult because of certain arrangement of the amino acid in the active site of lipases. So I could say that we failed to do the lipases for Candida antarctica B, but I think we're going to work again, because after we studied the aldoketoreductase and ligases, we have more information that we've been able to use to work back on our lipases. So this is one of the example, the human aldoketoreductase that normally not known to catalyze any of the reaction. Then I think this one is about 300 more amino acid, then we reduce the first one to about 16 amino acid in the active site. Then we start to make it smaller and smaller so that it can mimic the peptides. So we have the 16 amino acid, then we reduce into half, 8 amino acid, then also again try to reduce to 5 and 3 amino acid, and some with the different functional group. As you can see from here, that for the aldol reaction catalyzed by 8 amino acid, or we call it the octapeptide, we've been able to get a very high yield, about 97%, and the most important is the asymmetric, where we've been able to get about 97%. And based on this, however, we are not able to show the correct structure because the peptide is very flexible. Still have a random structure, but we're still working on that in order for us to get what you call this, to crystallize the peptides. And other than that, it is more like kind of a proline like catalyst that we have confirmed some of the mechanism. And recently we just published actually in PLOS One.
You've got 2 more minutes, Prof.
Yeah, in the mimicking lacase, where we know that lacase mainly normally they use normally takes about 5 to 7 days to degrade phenols or xenobiotic. But in our work, we've been able to show that the lacase that we reduce, we actually screen more than 20 lacases through computational way, and then we identified that certain lacase, in this case Trametis versicolor, and from there again we start to narrow down, and at the end we got about we have a selection of 9 until 4 amino acid, but some of the 4 amino acid we interacted it or complex it with the metal, particularly copper. Then we've been able to show that it's a good indication that it gives an oxidation, for example, from benzyl alcohol to benzaldehyde. And the most important is actually degradation of xenobiotic in less than, I think, 18 hours. So we get a very high, up to 80 to 85% of degradation of xenobiotics. So finally, I would like to conclude that this sustainable science is very important, and we start to have a new adventure with many proteins or peptides, where we know that it's not easy to work with enzyme. So what we can do is to try to minimize it. Other than that, we also now focusing on the artificial biocatalysts or bio-inspired materials, where we can apply, for example, right now we are working on using the amino acid backbones from the enzyme inside of our material. And finally, of course, molecular simulation help us a lot in understanding more about the biocatalysis and also the biomedical application. So the end, I would like to thank the organizing committee for organizing this. I think this is very perfect during this COVID-19, and I think it's very smooth as well. And particularly for Prof. Benny Pinantawan that I met few times during MIPANET and MDSM Malaysia. And also there are many other university, for example, the Udayana, Mataram, ITPS. Yeah, thank you very much. And there are many collaborators that work with me. Here are my collaborators, and the students that already, some of them, I think all of them already graduated that I use my works. And basically this is my research group. So I think quite common right now when you see more ladies compared to the gentlemen. So we hope to get more gentlemen and yeah, whoever like interested to come to UPM, you are welcome. And for that, I would like to say thank you very much again. Terima kasih. So I pass it back to the Mr. Chairman. Thank you.
Thank you very much for a very nice and interesting presentation, Prof. Basha. Okay, so now we move to the last speaker, but certainly not the least speaker for our plenary session today, and it is Professor Dr. Benjamin Chirsil from Prince Songkla University, Thailand, who's going to be speaking, and her presentation today is entitled Production of Biodiesel Feedstock from Lignocellulosic Biomass by Oleaginous Fungi and Yeast. So without further ado, the floor is yours, Professor Chirsil. Professor Chirsil, are you still here? I've seen her name, but I can't find it now. Okay, she's here.
Hello.
Yes, we can hear you.
Oh, okay. Sorry, I have problem with my internet. Okay, I will share my.
Oh, we've lost her again. welcome back.
Okay. Good morning. Can you hear me now?
Yes, I can hear you clearly.
Okay. I think I already shared the slide. So can you see the slide? No.
Yes, I can see it.
Okay. I will start my presentation. And really sorry for the unstable network. Okay. Good morning. My name is Benjamin Chensin, and then today I would like to present my research. Actually, it's the research from my doctor student, Miss Lavisala Intersit graduate. And the topic is the production of biodiesel feedstock from lignocellulosic biomass by original fungi and yeast. Okay, I think everyone already know that we need a lot of oil feedstock because there are a lot of increasing consumption of the oil all over the world. But the problem is the production of the oil, because we just ran out of the fuel, and then we need to find another alternative oil feedstock. And our group focus on the oil from the original microorganisms. Actually, yeast, fungi, microalgae, and bacteria can accumulate lipid in their cells, but not all of them is the original species. The one that can have high lipid content, higher than 20%, are defined as the original species, and then we can extract oil from the cells. And normally, most of them can accumulate
I'm afraid we lost her again.
Maybe there are some questions from for Prof. Basya.
Okay, maybe while waiting for Professor Benjamin to regain her connection, or she's here already.
So sorry for network. I don't know why. I to continue. So actually, we are interested in the Yaluet lipolytica because they can assimilate various kind of carbon salt. So hopefully you can hear me, right? Okay. Okay. So can I continue?
Yes, you can. We can hear you.
Excuse me.
And
The screen sharing. Yeah.
Yes, the screen sharing is working.
It's working.
one of biomass. I already shared this one.
Yes.
Okay.
I can see it.
We are interested in the lignocellulosic biomass from the palm oil industry because there are abundant the cellulose and hemicellulose that we can use as the sugar feedstock for the microorganisms. And this is the empty food bunch that left at the industry. So we isolate the fungi that can hydrolyze the lignocellulosic biomass and accumulate the lipid in the myceliums. And then in 2014, we published one publication for the Origenes fungi. You can see the lipid global in their myceliums. The fungi have the advantage because they can excrete the enzyme to hydrolyze the lignocellulosic biomass, and then they assimilate the sugar to produce the lipid in their cells. So this is our proposal. So we would like to use the Origenes fungi to produce the lignocellulosic enzymes, and then we use this enzyme to treat the biomass, so we can get the sugar, and the fungi will use the sugar to accumulate lipid in their cells, and this lipid can be used as the biodiesel feedstock. And the objective of this study, we are two main objectives. The first one is to pre-treat the lignocellulosic biomass, and the second one to produce a lipid from the pre-treated biomass. For the first one, to pre-treat the biomass, we use the Origenes fungi, and we also use the wastewater from the palm oil mill industry to add the moisturizing agent and also the nutrients. And we found that when we use the non-sterile one, the fungi can grow better and accumulate higher lipids and also produce the higher cellulose. And this is the biomass after we pre-treat with the fungi. So the structure is more soft, and it can be easily to hydrolyze by the enzyme to produce the sugar. And then we compare the time course of the pre-treatment. We found that at 10 days, the fungi can accumulate the highest lipid. But if we extend the cultivation to be 15 days, we can get more enzymes. And to be available at the site, so we need to optimize the operating parameters, such as how the volume of the effluent that we need to add in, and also the frequency, how many times we need to add during the cultivation. And this is the result. So we vary the volume of the wastewater that we need to add the nutrients by 50%, 125 and 200. And also we vary the feeding frequency every day, every 2 days, and every 3 days. And we found that if we use too low volume of the effluents, so the moisture content is not enough for the fungi to go and excrete the enzyme and also accumulate the lipids. So we need to increase the volume of the effluent to be 125 and feed every 3 days, so we can get the optimum moisture content, allow 82%, and that is optimal for the fungal growth, and it can accumulate the highest lipid yield. But for the enzyme production, we need to add more the effluent and every day, so we can get very high moisture content and higher cellulose and silanase production. And after the pre-treatment, so if we concentrate on the cellulose pulp after the pre-treatment, we found that we can reduce the lignin in the biomass and also increase the cellulose content. So this one will be suitable for the next step to produce sugar for the lipid production by the yeast. And in this paper, we propose the potential of the repeated batch solid state fermentation. So after one cycle, we remove 50 and 90%, and we compare the efficiency between 50 and 90% of replacements. With this fermentation process, so it's possible to effectively and continuously produce the pre-treated biomass, lipid, and enzymes. And we can do the continuous fermentation without the time consuming for the inoculant preparation. And this is the result. So we found that the fungi can grow very well until the 4th cycle, but for the enzyme production is reduced. And this is the table 6 show the solid fractions. So we can continuously produce the biomass with the cellulose content higher than 50%. But for the 4th cycle, the cellulose from of the solid fraction is decreased. So I think maybe only 3 cycles is effective for the fungi to pre-treat the biomass. This is the at the result at the 90% of the treatment. So the 90% is mean that we add more nutrients, we add more substrate, so we can get higher lipid yield and also the enzyme production. And for the solid fraction, it's also effective only the 3rd cycle. So we can conclude that the fungi could pre-treat the biomass effectively and produce lipid and enzyme. So we can use this one as the valuable byproduct, and is also effective in the repeated batch fermentation until 3 cycles. And then we compare the production of the lipid with another study, and we found that our study also show high lipid yield and enzyme production than after study. So it's possible to use this one to pre-treat the biomass and produce the lipid at the same time. This is a conclusion. So we use this fungi to produce the lipid cellulase and pre-treat the biomass to get the softer structure, lower lignin content, and higher cellulose content. And the repeated solid state fermentation is effective to produce higher lipid and higher enzyme production. And then you can find more detail in the publication in 2020 in BioResource Technology. And this is the second part. The second part is the use of the pre-treated biomass to produce the lipid by the yeast. We compare between the 2 processes, is the separate hydrolysis and fermentation. So we call in short HF, and another one is simultaneous saccharification and fermentation. In short is SF. For the first step, so we in the HF, we need to hydrolyze the pre-treated biomass by the enzyme to produce the sugar before we do the fermentation by the yeast to produce the lipid. So we need to optimize the hydrolysis parameter, so the hydrolysis time, enzyme concentration, and the biomass loading. And we use the RSM to optimize the conditions. And then we found the optimal condition for the sugar production from the pre-treated biomass. We use this one to hydrolyze the biomass and get the sugar. And then we use that sugar to screen the several origins yeast. And this is the result. We found that all the yeast could grow well on the sugar from the biomass hydrolyzed. But only one yeast, the Lipolytica, that can accumulate high lipid content more than 40% and also give higher lipid yield than other strain by 30 milligram per gram biomass, per gram sugar. And then the next step is the HF process. So this process, actually there are 2 processes. The one is the enzyme hydrolytic process. So this one will enzyme will hydrolyze the biomass to produce the sugar. And then the next step is the fermentation by the yeast. So actually when we want to do this, to get the condition for the enzymatic hydrolysis and the yeast fermentation should be very similar. You can see that we can use the HF for the production of lipid because the enzyme production and the yeast fermentation have similar pH range, so about 5 to 6. Although the temperature is just different, so the enzymatic hydrolysis is the suitable one is 50 degrees Celsius, but the yeast fermentation is only 30 degrees Celsius. So we need to do the pre-hydrolysis steps because, as you already know, the yeast need a certain amount of the sugar to accumulate lipid. So we optimize the several parameters, and so the HHF have the advantage because it's a one-step process. The process time will be shorter than the HHF, and we can reduce the end product inhibition to the enzymatic hydrolysis and also reduce the substrate inhibition to the yeast cell. And this one is the variable that we optimize by the RSM is the pre-hydrolysis time, cellular concentration, and the substrate loading. And this one is the optimal result. So after we get the optimal result for the HHF, then we use the yeast that we already screened and the optimal condition, and we do the fed-batch fermentation to increase the productivity. And in this step, we also compare between the sterile and non-sterile one. And this is the result. So when we do the fed-batch fermentation, so we can increase the lipid production, but just only the first time that we add the first and the second that we add the substrate. But for the third, we cannot increase the lipid production anymore. So we just consider about another nutrients. So we add the nitrogen salt together with the new substrate. And we found that we can increase the lipid production more than 9 grams per liter. And the lipid yield is also maximum is higher than 50 milligram per gram substrate. Okay, and then this we compare the production of the lipid by the yeast, and the lipid yield is comparable between the yeast in this study and another study. And then we try to optimize the process by make it easier to do at the industry. So we do the consolidated bioprocess for enzyme and lipid productions. So actually our fungi can pre-treat the biomass and it's also produce the cellulose. So we use our fungi to pre-treat and then to excrete the enzyme, and then we use that enzyme to hydrolyze the pre-treated biomass to produce the sugar. During the first step, when we use only the fungi, we can produce lipid yield only 22 milligram per gram substrate. And after that, we add the yeast. At the second day, we found that we can produce the lipid more, and then the lipid yield increased to be higher than 42 milligram per liter. It's comparable to the previous result that is allowed 50 milligram per liter, but we don't have to add the commercial enzyme. We can use the enzyme from the fungi. So it's possible to produce the lipid by the consolidated bioprocess between the enzyme and the yeast enzyme production and yeast fermentation. And this is the conclusion that when we do the pre-treatment, we can get the lipid from the fungi at the first step. And in the second step, we can use the same fungi to produce the enzyme in the lipid production by the yeast. Okay, and then we can get the comparable lipid yield, so we can reduce the cost of the commercial enzyme that we need to add in. Okay, and all you can find in detail in the publication in the BioResult 2020. Okay, and sorry for very short and unstable network. So thank you for your attention. So if you have any question, please. I cannot, sorry, I cannot hear anyone. I cannot hear.
Yeah, me too, I cannot hear. Looks like Dr. Mantiri is talking, but we cannot hear you, Dr. Mantiri. even I have problem cannot see the presentation of Prof. Benyamas.
Oh, okay.
Oh, yeah.
Sorry, host, can you hear my voice?
Yes, yes.
Okay, so we have several questions here, a few questions that have been submitted. The first one is to Prof. Basya. What method were used to analyze content of metals inside the cells? That's the first question. Would you like to answer that first before I continue on to the next question?
I think maybe so he means about the lipid extraction, right? Actually, we use the chloroform and methanol to extract the lipid
okay.
from the cell.
Okay. Yeah. Actually, yeah, that question was.
So I answer the question.
Yes, please, Prof. Basya. Yeah.
Okay. So for the one that inside the cell, we actually using what you call these the computational method. Yeah. So I think SVPROT, if I'm not mistaken. So the work that I presented just now is mainly on the in the computational work, not the experimental work. Yeah. So I think we use the SVPROT, and there are several other metal detection. And the best thing is we are using all the web-based, which is actually free, that anyone can work on that. I think I cannot remember, that works quite long ago, 2013, 2014. Okay.
Okay. The second question is also for Prof. Basya. So it's from Laurensi Sasube. The question is, I really am interested with your presentation, especially about active site at biocatalysis. As we know, in SARS-CoV-2 receptor, there are many active sites in database of the proteins. In your opinion, which one is the best active site for testing in molecular docking study? That's the question.
Right. Okay, thank you. It's proteases. But I cannot remember as well. There are several proteases, but there is one or two that people been focusing on. But the protease of the virus, yes, I cannot remember exactly. But there are two, if I'm not mistaken. But I cannot remember the exact name because I'm not working on COVID-19. But my colleague is working. I think I will contact Professor Laurensi later on.
Okay. Thank you for the answer, Prof. Basya. And the third question is for Professor Benjamas. It's from Niluputumandi Widiyanti. The question is, where is the larger percentage isolation of oil from lignocellulose compared with whole of plant cells? Did you get it, Prof. Benjamas?
Hopefully I think I should get it. Okay. I think as the oil from the palm empty fruit bunch is allowed 10%. So when you want to extract the oil from the palm empty fruit bunch, right, it's allowed 10%. But for the microorganism is if we have the 100 gram of the cell, so we can extract is allowed 30 to 40 grams. So it should be allowed 30 to 40%. So based on the biomass, the microorganism can produce higher lipid yield.
Okay. So the second question is for the second question for Prof. Benjamas is, I want to know the name of the species of oleaginous fungi and yeast to be used for fermentation of the production of biodiesel.
Actually, the fungi is Aspergillus tuberinogenesis, and the yeast is the Yellowia politica.
Okay, so that's the name of the fungi that you use.
Yes, the fungi and yeast.
Oh, fungi and yeast. Okay, thank you. Also, the next question is for you, Professor Benjamas.
Yes.
What kind of palm that give the highest microbial lipid production?
Actually, I use the empty fruit branch empty food plant because it's most abundant biomass from the industry.
Oh, okay.
I didn't compare between the type of the biomass from the palm, just only the empty food plant one.
Okay, all right. Okay, since there's no more question, maybe they're still writing down the question. I have a question for Prof. Basha. I'm interested in your research regarding the formulation to reduce the inflammation of COVID-19, which you find that the site that has the largest effects in the interface between alveoli and bronchus.
Yeah.
My question is, do you use natural derived anti-inflammatory or only the synthetic ones?
Yeah, okay. So that work is actually what we plan to do, but because of what you call this, most of the lab right now being closed. So we actually, for the cancer therapy, we use two drugs, dual drugs. One is curcumin, and which is actually this natural product, and another one is docetaxel. And since we'll be able to control both of the nano formulation, so we opt right now if nanocurcumin can be used for the COVID-19. But of course, with a certain, but still you have to control the size of the nano emulsion so that it can go to the targeted, or especially in the smaller one, alveoli, and so on. Yeah. So we haven't tested. We already have the formulation, but yet to be tested because I don't have the BSL-3 lab, and in Malaysia, the what you call this, we are not able to conduct the COVID-19 test in the university. So I have to send it to the Institute of Medical Research in Malaysia because they are the only one that have the rights to do all the COVID-19. So yeah. Haven't tested it yet, but we hopefully that it works that way.
Okay. Yeah, the reason I'm asking is because here in our university, there are a lot of research that we try to explore the use of natural products as natural derived anti-inflammatory agents from our endemic species here. Or maybe I'm sure in Malaysia people are doing that too. But so maybe at some point, if you already do the test, we can collaborate with the products that we get from our research.
Yes. I'm very happy as well to collaborate with many Indonesian fellow or the Thailand, or all over, because like in Malaysia, I think they have the Malaysia-Indonesia Research Consortium, something like that. Yeah.
Okay.
And of course, there are many for the ASEAN. So yeah, we look forward for that like kind of matching grant from both university. So yeah, please, if you can email me, then we can discuss.
Okay, great. Thank you.
You're welcome.
So since there is no more questions in the chat pane here, and it's 12 o'clock now, so maybe that answer from Professor Basha concludes our Q&A session for today. So since I am the chairman of the conference, it's now time for me to say thank you to the people. So on behalf of the organizing committee, we would like to thank everyone who made it out to our first international conference that we called International Conference on Natural Sciences, Mathematics, Applications, Research, and Technology. And we've come up with a good name for this, is Icon Smart. And we would like to thank especially to our rector, Professor Ellen Joan Kumat, for her continued support to the Faculty of Mathematics and Natural Sciences. This actually is the 4th year of our faculty organized international conferences, and it has brought a lot of opportunity for both UNSRAD both our university and our faculty in terms of national and international collaborations and number of published papers in reputable international journals and proceedings, such as IOP. And we would like also to thank all the incredibly inspirational and talented plenary speakers who have delivered brilliant and thought-provoking presentation. Your contribution to this conference have been exceptional. Thank you very much. And as a token of our appreciation, we would like to present the certificate for the plenary speakers. Host, please. Oh, okay. There's some technical problems, so we will present it later. So we also like to thank the deans and the former dean of the Faculty of Mathematics and Natural Science from partner universities who will present as invited speakers in parallel sessions after the lunch break. For the parallel session, we have pre-assigned the participants in breakout rooms corresponding to their tracks or their field of interest. And for now, we will have a lunch break that will be provided in the dining room of our own house, of course. And at 1 o'clock, Manado time, or Central Indonesia Standard Time, PM, we will meet again in the break rooms. Have a nice lunch and stay healthy. Thank you very much. Thanks again, Prof. Basha and Prof. Benjamin. Very nice and interesting talk.
Thank you very much. You're welcome. Terima kasih.
Yeah, terima kasih. If it's offline conference, we will have a lot of discussion.
Right. Okay, thank you.
So again, for the participants, we will meet again at 1 o'clock Manado time, 1 o'clock WITA, Central Indonesia Standard Time. And all you will do is get into this same room, and we will automatically break the rooms into breakout rooms. So you don't need to do anything. We will do the transferring to the break rooms. And please don't forget to rename your name with the letter A, B, C, D, etc. according to the room that the organizing committee has given you through the email and the Telegram group. So the committee has already assigned your name with a letter A, B, C, D, etc. according to your field. So please do put, like for example, if I can rename my name, I will put B dash my name, Feki Mantiri, and then the committee will know where to assign you, because we've got nearly 200 people here. So it will help the committee a lot if you put the letter that we send you through email. Thank you.